So I put up a video that shows everybody how to convert from base 10 to base 2 and base 2 to base 10. So this is how you would write a positive integer, any positive integer in base 2. So what I decided to do here is, while I'm on the subject, put up a video that shows you how to convert from, or how to represent a negative number, which is not at all obvious, right? Like, would negative numbers be represented? Now, why do we need a negative number? Well, negative numbers in computer science are useful because you don't have to supply or create a subtraction circuit. In other words, if you wanted to subtract, let's say, 4 from 6, 6 minus 4, you'd have to create a subtraction circuit. But if you didn't have a subtraction circuit, you only have an adding circuit, then all you have to do is take 6 and add a negative 4. Same thing, right? So it turns out it's much faster to add and represent numbers that are negative in a special way than it is to create a subtraction circuit. And speed is of the essence. So I'm going to show you how to convert or how to represent a negative number in computer science. So I'm going to go over to the whiteboard, because it's another whiteboard thing, and I will demonstrate. So let's make up a random negative number. Let's say negative 12. We want to represent negative 12. Well, one way you might think of doing this is to represent 12 using binary. So you remember the place values are, again, the 1's place, the 2's place, the 4 place, the 8 place, and the 16 place. I'll stop there. And you say, well, how do we make a 12 out of this? Well, we need an 8 and a 4. So 8 and a 4, and then that's exactly 12, and then these become zeros. But that would be a positive 12, right? Well, one thought might be, well, what if we just use this left bit here that's not being used, the leftmost bit, as a sign bit? So for instance, if it's negative, it would be, let's say, in this case, a 1. But if it's positive, it might be a 0. So this, unfortunately, using this particular method, it doesn't work, because there's no way the computer could understand this to be a negative 12. Furthermore, if we tried adding this to a positive 12, if we added the bit pattern of 12 to this negative 12, 12 again is a 1, and the 8's a 4, and a 0 over here. And if we added this bit pattern together, in other words, these two bit patterns, if we added them, well, what do we get? We get a 0 and a 0, which adds up to a 0. A 0 and a 0 adds up to a 0. A 1 and a 1. How much is 1 plus 1? Well, 1 plus 1 is 2, but 2 in binary is 1, 0. So what does that mean? That means we put down a 0, we carry a 1. Now, what about a 1 plus a 1 and a 1? That's 1 plus 1 plus 1 is 3, but 3 in binary is a 1 in the 2's place and a 1 in the 1's place. So that's a 1 and a carry bit of a 1. And now we have a 1 and a 1, which is 0 and another 1. So that's certainly what you get here at the end is not 0, right? So remember, plus 12 and minus 12 should add up to 0, and that's certainly not 0. So this particular way of doing it doesn't work. So I'm going to show you the way it actually works. So the way it works, we start again. The algorithm for converting, this is known as 2's complement notation. And this is the way negative numbers are represented in computers and in calculators. How does it work? So I'm going to show you this through an example. So let's say we want to do negative 12. So to do negative 12, step 1 is to start with a positive 12. So we just saw positive 12 is a 1 in the 8's place, a 1 in the 4's place, no 2's, no 1's. And I'm going to put a bunch of zeros here on the left. So remember, when you're representing a number, you have more than 4 bits. So in this particular case, let's say we work with an 8-bit representation. So that would be a positive 12. So ultimately, we're interested in negative 12. So we start with positive 12. Second step is to flip the bits. All the bits get flipped. This is the process known as 2's complement notation. So we're going to flip all the bits. What does flipping a bit mean? It means 1's become 0's and 0's become 1. So we flip all the bits. 1, 1, 1, 1, 0, 0, 1, 1. So that's really fast, really easy to do with a computer. Single pass through an inverter switch. And then the last step is to add 1. That means add 0, 0, 0, 0, 0, 1. So this involves the addition process. So adding means what? Well, again, 1 and 1. 1 plus 1 is 2. But 2 in binary is 1, 0. So that means you put down a 0 and you carry a 1. So remember, we're adding right here. Let me try to focus here. We're adding right here. Right, so the original number, we flip the bits, and now we're adding 1 to the flip bit representation. So 1 and 1 is a 2, and 2 is 1, 0. That means the next, we put down a 0 and we carried a 1. Second place over, same thing, 1 and 1. Put down a 0, carry a 1. Here we have a 1 and a 0, that's just a 1. Here we have a 0, here we have a 1, a 1, a 1, and a 1. So it turns out that negative 12, this is negative 12. Now, the interesting thing is it doesn't look like negative 12. It doesn't look like a 12 at all, but it behaves like a 12. For example, how does it behave like a 12? Well, in the computer, it does. So for example, if we take 12 and let's say we want to add the number 14, just good old number 14. Well, how do we represent 14? Well, let's think about that. So 14, we have, again, the place values, the 1, 2, 4, 8. 16 is too big, so we need an 8. We need a 4, that's 12. We need a 2, that's 14, and no 1s. So a 14 would look like that, right? Those are all zeros in 8 bits. So again, this is the 1's place, the 2's place, the 4's place, and the 8's place. That adds up to 14. So there's the representation of negative 12, and there's the representation of positive 14. Now, if we add those together, we know as human beings that we should get the number 2. Let's see what we get. So we're going to do binary addition again, where you add 0 and 0, you get a 0. You add 1 and 0, you get a 1. And over here, we get a 1 and a 1, right? Well, 1 and 1 again is 2. 2 is 1, 0. So you put down a 0, carry a 1. And you keep doing that, right? 1 and 1, 2, put down a 0, carry a 1. 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 Put down a 0. And there's only 8 bits. There's no 9th bit. So there's no place way over on the left-hand side. There's no place to carry that last 1. So this is true of any computer. A computer is a certain number of bits. Your computers you're staring at that you have at home are probably 64-bit computers. So there is no 65th bit. There is no place to carry it. So there's only a certain number of bits in that particular circuit, and there is no additional bit. So there's no place to carry that leftmost 1, and therefore what we're sort of exploiting that fact, and look what we have here. We have the number 2, which is exactly what negative 12 plus 14 is. So that's giving you a rough idea. I know it's pretty rushed, and there are other examples of this on the Blackboard PowerPoints. But again, this is not on your test, but this is for computer science majors who might be interested in electrical engineering or software engineering, or going to take the computer architecture course and want a little bit of a head start. You can take a look at this. But for the rest of you, this is not on the exam, because I think it's a little too tricky and it involves too many questions that students usually have when I do this live in class. So I hope that is helpful. Anybody who's going to major in computer science and possibly computer engineering.